Hi all, this is Claudio from FEA.com, bringing you another live stream related with finite element analysis in biomechanics, namely in dental aspects. Let me firstly share my screen. Salutations to people who waited for me. I have a message from Hassan. Hello. All right, so a quick reminder about our website, where you can find lots of simulations, books, tutorials, and very important, the biomechanics page with lots of very interesting, complex, and easier FEA, even though they are nowhere to be found elsewhere on YouTube due to their complexity and knowledge required for its modelization. So, firstly, let me go on GrabCAD and show you what chance we have to produce such 3D models. Let's go with most light, and we're going to look for, not exactly for teeth. We can go for teeth, but in today's scenario, I'm not going to simulate separate teeth. We're going to take it from zero with a beginner approach, because, as I said before, my first desire is to attract beginners and young people in order to be, let's say, pleasantly surprised by this domain and to find satisfaction and what they need in this domain, namely biomechanics, FEA, and ANSYS software. I opened, for example, this model, which is shell. There is nothing like step or parasolid, only STL or OBG, which they are shell bodies. Look here. Let me prove this to you. Let's explode a little. Yeah. I don't like this model because it doesn't. The teeth do not have roots, and both the mandible and the jaw, they're not, let's say, fully detailed. So this is not what we're going to use today. We're going to use something more similar to what you see here, skull head with joint teeth. Also, not 3D models, so they are, at this moment, these models that you see on GrabCAD, they require additional work regarding the so-called solidification, because they are, so it cannot be exploded. This is a single STL part. Let me tell you. I will download it in order for you to see. Let me open Space Claim. So I was talking about Solidifying. The STL and OBG files, these are mainly modeled using software like Blender, Maya, 3D Studio Max, and the same. They are shell. They are only surface bodies, and in FEA software, we need to make them solid inside in order to make the solid mesh, then apply boundary conditions, and so on. So I kind of wanted to draw your attention to the fact that searching for teeth, it will throw us in the realm of gears. So it's not so much useful. Maybe we can try human teeth. Let's see. Yeah, so let me just teeth. Look here, plural, and he gives only one tooth. Yeah, which is not okay. Let me show, for example, what we have here. We also have joined or fused. The jaw is fused with the teeth, except maybe this one. Let's see. It cannot be exploded. Why? Now I am going to show to you. Let me download it, and I will show to you why it cannot be exploded. Let's like it because it was work, and we appreciate work. Space claim, and can we go for desktop? Let's see if we have a desktop. We have a desktop here. I'm going for the folder view because I don't desire to always show my desktop. Date modified. Practice Mandible, for example. This is practice Mandible, yes? You can see in the background. Why it cannot be exploded, let's say, yes? Let me show it to you. Firstly, we can clearly say that they are fused, but maybe this is separate, maybe. How do we find this? It's very easy. This is a shell body. You can see it here. It belongs to the facets toolbar. Yeah, so we need to kind of solidify it. Right click, separate all. And if this is an assembly of facets, so this is an assembly of surface bodies, then they will be separated. So unfortunately, there is no, it's just one part. Even this one is also fused. So he scanned, I think, this implant together with the other teeth and the jaw here. Have too high hopes regarding the models from GrabCAD, and I will offer you an alternate solution, an easier one for finding 3D models. This model, also I downloaded it a few minutes ago from GrabCAD. This is very promising. Why? The mesh is extremely nice. It's very uniform and almost perfect. It's so beautiful. I'm talking about the uniformity of the triangles from the mesh. Look here, this is facets. What we do, we can clearly see it's a single body, a single part, let's say. We cannot explode it. But we know that if we right-click separate all, look here at all the parts, yes? So we have separate teeth, let's say. This is a very nice model with a small caveat, yeah? The caveat is they have only one root, also for the molars. Here should have been maybe 2, 3 roots, and it's only one. This is the small caveat. Otherwise, if we are not interested in detail to go for all these, we can use this 3D model, no problem. I think I will not use it today because the shape is a little weird. It needs to be kept in mind, yeah? We can already see some interference here, so we need to unclench because it's kind of harshly clenched together. This is how a shell should work, all right? Let me keep it in background because I want to direct your attention more to this. This is what we're going to use today, all right? Because I'm not interested in the teeth today, we're going to be interested in the biting and the chewing. I'm not interested at this basic scenario, in this basic case. This is what I'm interested in. And what I have done, it's also taken from GrabCAD, but I will not search for numerous dozens of pages until I find it. this here, a lot of work is already done. You know, because a lot of work is already done, maybe it's not so useful to you. I'm thinking maybe let's work a little with this, just for fun. But it will not have the realism, the shape of this. This is a very realistic 3D model. Let's see. 1 second, let's see if there is any message from the live stream. No message except from Mr. Hassan, which was who was waiting for this live stream. So, because I would like to impart knowledge and share with you various methods, let's, at least for the beginning, let me take you through the steps of solidifying this. The easiest way to solidify, of course, is right-click, convert to solid. And here I advise to go for merge faces. Yes? What we will obtain? Convert a facets body can greatly increase the size of the model. Are you sure you want to continue? Of course, this is the purpose. Let me show you the disadvantage of doing this. Solidifying, or let's say filling with material, such a 3D model has the main disadvantage of keeping the triangles, keeping these facets. So our 3D model will inherently and I don't know, mandatorily, forcefully will have these facets. And these will, one, impose the meshing. For example, we desire to make hexahedron dominant mesh. It's not possible because the facets will still exist in the 3D model. All right. So this is one main disadvantage: the fact that the facets will command. It looks very nice because the model was very nicely done. We cannot go these facets. We cannot delete them or smoothen them somehow. We cannot smoothen them. Because we are here, let me just try something that now I have in mind. I was thinking about making this as a surface body. Look here, this is a solid model. The easiest way to make it a surface body, click on one facet or face and detach. And this face, this small patch, will be detached from the rest of the surface body that you will see in a few dozens of seconds. Yeah, so we have this small patch and the rest. Why I wanted to is because I would like, for example, here on tools, to go for auto scan. Remember this command. Mother of all commands when working for solidifying and smooth bodies from shell bodies, all right? So remember this command, auto scan. Let's see if auto scan on the surface body and something like this. It wants a faceted body. All right. So it does not work like this. Then let's undo. We cannot, at this moment, we cannot smoothen this. We cannot make these triangles and quads disappear. All right. Let's see if I hit undo again. If I have again the body. Yes. So I told you there is this command, tools auto scan. And let's click on the big hide other bodies. Let's see if this command works here. Yes, click. and check. I think it will work because the geometry is so nicely done by the modeler. So remember, this is the purpose. We need to have very smooth faceted bodies, very smooth meshes regarding the uniformity of the triangles. And this uniformity of the triangles will ensure a successful autoskin operation. A not so successful autoskin operation will either result in errors or it will leave holes. It will leave unskinned patches if there is not a high degree of uniformity regarding these facets. So in a few seconds we will see what happened. Let's hide the facets body. And this is transparent. Why? Because this is a surface body. Yeah, it's not a solid model. If it's a surface body, for example, if you pay attention, you can see here a hole. Yeah, as a missing patch here. Also here, a hole, a missing patch. How do we attempt to correct it? Here also a hole. How do we attempt to correct it? The repairing for such surface bodies is made through the repair toolbar. There is also a toolbar to repair faceted bodies, this one, facets. So the difference between these two facets is only referring to mesh bodies. Here I'm talking about STL, OBG, and so on. And here I'm talking about surface bodies. CAD bodies, let's say, but surface, yes? So always assume when you have such transparency and we have clearly surface bodies, always assume, escape from the command, assume always that we have missing faces. Look here, we have 5 missing faces. We can rotate and kind of look at them. They are pretty symmetrical, let's say, because the model was very nicely done, except for this small patch. We can click on them manually, separately, but let's just click the green check mark. This is what we need, all right? Instead of the millions of facets or small triangles, we need such a solid body. This is a solid body, yes? This is the original faceted body. Now we can delete it, the original faceted body. Yes, we can delete it. We have this one. Let's continue. Why not? Let's continue with this in order to share with you the whole process of solidifying meshed parts. I will write here 2026, January 25, skull with head, joint teeth. Yeah, but V1 here. A good approach is always to right-click, source, internalize all. In this way, you will ensure that you have a proper version without inheritance, without parents or something else. So I repeat, source, internalize all. Save. The other bodies. What bodies do we have? Why is this still here? It should not be, because locating structure 3, delete, because I have the 3D model. I don't care for that part. All right. So we are here. Again, we have the auto command. Now we can do, you know what? We can apply the auto scan command, something like this. Instead of clicking the green mark, we can Control A. We have select all, for example. Select all, do we have? Yeah, select all. Or Control A. And we can click the green check mark. We can do it on this very nice model. we cannot do it for the awful and the horrendous models that exist on grabcad.com. 95% of them, they are wrongfully modeled and horrendous looking, because just they are for show, they are free, nobody assumes responsibility for them. Yeah. So if the geometry were to be non-uniform and wrongfully made, when the first error appeared, it kind of entire command. This is what I would want to say to you. Yes, the method of selecting all the parts goes and works only for such high quality models. But for the other models, for the horrendous models, I advise to separately click. Look here, yes? So because of this, these errors, the entire AutoSkin model, the entire AutoSkin command will be abruptly stopped, let's say, yes? So for example, AutoSkin, Control A to select all, and if I click here, it begins to AutoSkin. Maybe there are some very well-made teeth, but because there are errors on the jaw, the entire command will be stopped. So, and wasting time, let's say. For example, let it work, but it will stop the entire command. This is why I prefer to do the AutoSkin operation manually for better control of the process. Now I think it's the last one, the jaw, which I think it will stop the entire command. Yeah, look here. So we wasted 1 minute because of one error. Yes? We can do something like this because we know the problematic part. We can hide it, then resume the AutoSkin for all the parts, because I kind of know, we kind of see that these teeth are very well made, only the jaw has problems. And I think we can solidify them in a bundle. So, very nicely done. We have an AutoSkin that is missing a small patch. This means it's a surface body, is not a surface body, not a solid one. The software very smartly hid the successful parts, which it solidified. Let's also show this one. Why? Because I would like to click here and here with Shift pressed, hoping that it will work. All right. So let's right click and delete all of them. I'm wondering where is the, okay, it is here. All right. So again, click the top, click the bottom, right click, delete. You can delete manually, no problem. So now we have only solid parts and one surface body, together with the jaw and this tooth. I will not delete this facet body until I'm sure that I can heal this surface body. All right, let's hide everyone and let's show only this. And we're going for the repair command. As I told you, assume that faces are missing. In order to help the software to make this patch, look here at how many sides it has. 1, 2, 3, 4, 5, maybe 6 sides, very irregular. In order to help the software and not look here, for example, this is the missing face. I can do like this, and the shape sometimes will be very irregular. Maybe sometimes, look here, maybe sometimes it looks irregular, maybe, yeah? But what I would like to do is undo and enlarge a little, all right? Let's enlarge a little the scope. Delete, click and delete. And instead of 5, 6 irregular sides, we maybe have 1, 2, 3, maybe towards 4. And the probability of creating a very regular face is very high now. So we have the same, warning, a missing face, but the shape of the hole is very regular, complete. And it looks very nice, yeah? So we have this thing. What we have again? We have the jaw, and now we have that tooth we have just repaired. We can delete it, no problem. Let's save what we're doing. And here, jaw. This is the jaw. The jaw has problems. Yes, we have seen this. We can click here, check facets from the facets toolbar, and it will say mesh is self-intersecting. I presume here in the creases, in the crevices, maybe there are some self-intersections, some very sharp look here. Triangles which will, for example, look here. This is clearly a wrong self-intersection there. Let's go somewhere else. It's very important to understand how the software works. And what we're going to do is to help the software somehow, yes, yield good results. This is not good, right? So we need to take these into consideration. So we are here. We know we have some self-intersections. We can attempt an auto-fix, but from my experience, in 9.5 cases out of 10, it doesn't do almost anything. It's not so helpful, but let's just do it. Auto-fix a mesh. We can see that it kind of did something. Look here, these horrendous looking triangles. I'm not very happy about them. Yes. Let's check facets again to see if it improved something. Body contains non-manifold vertex. Yeah, whatever that means. So if I were to judge this, it worsened the geometry, because in the past we had some very thin slivers of faces, and now we have, oh my God, so many problematic faces. You know what? Let's ask for, and always assume that this is the main problem. Fix sharps. Yeah. Look for sharp edges and vertices. Always assume this is the problem. Besides, if we have holes, but in principle we don't have holes. But this is my problem. Let's click here. And it says 1,116 protrusions. And this is not so very happy, okay? It's not so very useful, because a few minutes ago when I attempted an auto skin, we had very little. We had very little such protrusions. Let me undo and show this again to you. we have more than 1000 protrusions, which in reality are sharp edges and vertices. And let's undo and see in the past how many problematic facets we have. Yeah, so I skipped the autofix. There is no autofix now. Look how nicely it looks, yes? With autofix it looked very... In this case, autofix didn't fix the mesh, all right? Here, let's go for facets and skip check autofix whatever and go directly for fixed sharps to compare with the 1116 arrows, yes? Look here, 145 protrusions, not 1000. So, as I told you, the autofix only worsened the 3D model. Here, just click the green check and hope that the problems will be solved. Hope. Click repeatedly and aim for 0 if possible. Let's see how much time it will take, and I think we might have hit a limit. Yes. All right. Again, let's look for other errors, you know. There are no openings. There are click faceted body to find self-intersections. Do we find self-intersections here? I don't know if it found. I don't see. Now we have 82 protrusions instead of the previous 30 something, 35, 33 protrusions. Let's ignore for a while. One over-connected edge or vertex. Let's attempt to fix it. And now if we're going towards 1000. Yeah, the previous 1000 sharp edges and vertices. Let's go again to fixed sharps. We have 82 protrusions. Let's attempt to repair them. Is it possible? I remember that in the past we had something like 30 something. We're back to 30 something. And let's kind of attempt to understand what can be done here. One small problem is we don't have transparency. For shell bodies, we don't have transparency. If transparency were to exist, then I would have looked inside. But workaround is we can switch to hidden line wireframe, and it does not work. This doesn't show the inside, or does it show? I'm not convinced that it shows the inside. All right, we were here at the 33 protrusions. Let's attempt to understand. Even though it might be very tedious for you to, and very hard to understand, we need to kind of to assess how the software thinks and where the problems are. So bear with me a few more minutes, please. If I attempt to make such a selection, the fact that I'm looking through walls is not so very helpful. So here I'm looking through this wall, big wall, in order to see inside. So I cannot select these facets, yes? In order to somehow delete them. Let's, you know what, let's do something like this, if it will work, but it does not work. Escape. For fun, can I do something like this? Yes. Now you'll answer yourself the question regarding why there are no decent, no useful, no complex biomechanical simulations presented on YouTube because of such modeling problems. Yes? So I'm showing you all these because I would like you to see the amount of patience and knowledge needed to correct such models and make them useful. Yes. So I'm deleting very small slivers and problematic face sets. In an attempt to get rid of the previously shown errors. Oh my God, now I understand there is like a pocket here, you understand? There is like a pocket and it cannot solidify. It's a problem with the Boolean interpretation of the space, let's say. Yeah, it's logical interpretation of the space. But we can hope something. Let's go here, delete, and look here at the pocket. There is this pocket, which which gives us so many problems. Oh my God. When encountering such modeling problems, of course, that most of the people will abandon such approaches, editing and everything, because you need lots of patience, knowledge, and belief that you will obtain the proper geometry. For example, this is microscopic one, yes? Just for fun, do I dare fill this hole? Fill these missing faces. Let's try and select all of them. I'd like to help the software not to have these jagged contours. This is why I'm deleting so many of these triangles. Yes, as I said before, we need a uniform missing face in order to be later filled by the software. Look here. Click here, here, and you know what? If this proves to be very problematic, because I kind of told you in the beginning that I'm using not the geometry, but for exemplification purposes, for editing purposes, I'm sticking at this moment with this geometry in order for you to see the entire process of healing it. For example, this looks very nice now. Do I dare to... let's see, there is a small atom or molecule of something. Let's go and see if I can delete it. I don't know. Can I? What is this? Oh my God. All right. So I have an opening here and an opening somewhere else. I don't know where else. Let's click on this. If I click the green, check. Then it will maybe heal an opening somewhere else. Now I'm focused only on this area. Hopefully it works, but I don't see that it works. I'm looking for the other opening, and you know what? Let's just click the green check. It filled the previous hole with such, oh my god, oh my god. You know what? Let's hope for the best. Yes. So, next, 29 protrusions. You understand now at this moment that we're not going to heal all the other 29 protrusions. Yes, it makes no sense. I'm thinking if we can do something about it. I would stick with this geometry because it looks, besides these errors, this geometry looks very nice. For example, can I do something like this? Yes, but we have this pocket which will be problematic again, because when I select this pocket, it also selects everything from behind. We can do this, and we will have an extra hole, an extra missing patch in the behind. Let's see if we can do this. Yes. Undo. Why do we have a section view? You know what? The best selection is with from the right to the left. Yes, right to the left. This is the best selection because it mainly it encompasses all the faces in the problematic areas. We need to zoom in for the small slivers and spikes which exist at an almost molecular level. And at this moment, many of the beginners have left the chat because the problem is so complex and it takes so much patience, attention, and knowledge. This is always the difference between an existing or a future expert and beginners, with which the beginners get tired very fast. I'm thinking about maybe deleting some of these facets to help with patching them. But you know what? Let's see. So they were healed. Another thing, 70 protrusions. Bear with me, please. So we have this this pocket, because it's clearly sealed here. I would like to remove the entire pocket. Escape command, and the pocket is this one. And again, rinse and repeat. So, dear audience, yes, if you are not live, you can always skip towards the end, towards where you see the model finished and analyzed. So now we're working on the molecular level. Oh my God. Yes. I love it because I have done such similar editing so many times, and immune. I'm looking forward for such problems to be solved. All right, missing faces. There is also a small whatever is this. Go for fun to this atom and delete it. Faces to openings solve. Or so again, there are no openings. So if you have patience, then yes, the model is kind of healed. Let's go again. Here, click a faceted body to find self-intersections. It doesn't say anything. One over connected edge or vertex. What the F is this? It comes from the self-sealing of this whatever pocket, how it's called. Can we heal it somehow? Let's see. Oh, it looks very nice. So, for example, I will undo to understand. So, we had this pocket inside, and when I'm healing it, there is no pocket inside. You understand what the software did? But there is a caveat. Let me undo. Before hitting this operation, the overconnected operations, when I'm looking at fixed sharps, I had 12 protrusions. I don't know if some of them, all of them here. No, they are also elsewhere. I have 12 protrusions, all right? Remember, 12 protrusions. Escape, and when I'm healing this, we will check the number of bad protrusions, the number of fixed edges. Yes, because I think these will add to the number of fixed edges, of sharp edges. Look here, 200 instead of 12. So 1 minute ago we had 12 problematic sharp edges. So undo. I will not go with this command, even though it's seducing, it looks very nice, it gets rid of this pocket. Instead, I will get rid of this pocket myself, yes? Which one is the easiest way? Which one? Let's go similar to what I had in the past, something like this. Can I rotate this? Where was, okay, here. Okay, let's take something like this, escape, and I propose to delete it like this. I said beginning from the right, because it goes through everything. This is the pocket, the problematic pocket. Let's see if I come from the left. No, it's not so nice. Let's go from the right. Is there any difference? I don't see any difference. So feel free to skip the hard work, yes? And I wanted to choose in the beginning I wanted to choose the easy way with the one using one of my geometries that I already I took something from GrabCAD and healed and solved everything, but I wanted to impart knowledge. So here we are on the atomistic level. Can I? Yes. So we have these faces, these missing patches. Can I help the software with something? You know what? Let the software do its thing, all right? All right. So, sharp 8 protrusions. What can we do here? Let's not go very in detail. Instead, again, let's delete the whole of this. If possible, select the tiniest, the thinnest triangles, the sliver, undo a little, right? I want to select only this one. Come on. I don't know how it happened. We only have one hole. Not. We don't have a missing face on the other side. We don't care. We're happy because we can solve it. Sharp edge, 3 protrusions. So we have something like problematic here. Let's delete this. Can I fill this? We have 2 openings. There is something like a mess there. Yes, now it looks nice. 2 openings. Come on. Where are the 2 openings? Both of them are here, of course. They are overlapped, and you know what? Let's say that we're correct now. 10 something. Let's delete these as we did in the past, something like this. 1 opening. Do we have problems here? Small problem remains. Come on. We need to select this. Delete, 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 delete. What is this? Come on. Yes. So what have we here? 2 openings. There are no openings. 6. Oh my God. All right. So it's not for the work that I'm doing. It's not for the lazy people. We need to be very stubborn in order to do this. All right, we have them at this level. Let's just delete everything here. Do we have problems here? 10 protrusions. All right. Yeah, we're solving something, and we encounter the other problems. Let's at least get rid of this error in order to get our mind from the other problematic faces. Come on. Let me select you, please. You don't want. All right. This triangle, this facet, I don't know why is this so problematic. All right. Why? Yeah, I think I lost it. Oh, I found it again. So I wanted this triangle to disappear, but I don't know how to orient it in order to properly select it. All right, so yes, finally, but what happened? This one I would like to delete, and hopefully we're nice. 18 protons. All right, and they are localized in another, only here. All right. So save. Yes. So we don't care. Let's delete everything that it is possible. In facing such problematic features, we need to be very trustful and almost heroical that we will solve everything. So this is why we need to keep our smile. We need to have our head held up, and yeah, to be very trustful, because this is what we need to have. Look at these small atomical facets. Whew. Finally. Do we have problems? There are no problems. Oh my God, I cannot explain I cannot convince someone to have this patience. Oh my God. So what we can do now? We can go to Tools, Auto Skin, and hopefully it will make it. There is this problem. If I have abused the editing too much, those problematic areas will not be filled, and maybe this model will result in a surface body instead of a solid part. Maybe. Let's see. Yeah, as I predicted. So this I do not need at this moment, the underlying mesh, but we have this thing, and the correcting this thing will be very problematic, I think. Repair missing faces, and this is the problem is it's so complex, and there will maybe make a blend that will damage so much of the jawbone. Yes, but we have a very easy workaround for this. So normally we should not attempt. We should not do this because you will see in a second. Look what it made it. Yeah, it have assigned this problematic surface. Only it created two other missing faces here. Yeah, here and here. So it's so complex. A very easy workaround is this one. Ctrl Z. Maybe you have already seen the workaround. I remind you that this is the missing face. This is a easy workaround. You see that the right part is made. The right part is correct. So my suggestion is, let's delete the left part. Yes. So can we align this? Yes. It's perfectly aligned. Let's go with a plane somehow exactly in the middle. We don't have like a perfect middle, let's say. Let's make a plane somehow here. We can take advantage because of the fact that the nature is not perfectly symmetrical. We don't work here with an industrial model. It's not perfectly machined or cast or perfectly symmetrical. Hence, we can use a slightly skewed model and an imperfect model, because this is, in the end, this is the beauty of natural creation, the lack of the imperfection, the lack of perfect symmetry. Perfect symmetry sometimes can be boring. So let's create a plane. How do we create a plane? Let's select at least one point. Oh, it's almost perfect. Let's make it as good as possible. We need the plane to be exactly on the right side. I don't like this, whatever this is. So let's maybe go from above and orient the plane. Oh my God, oh my God. All right, something like this, Let's move the plane towards left. 6. By the way, the scale of the model is not good, so I need to resize. It does not match the real dimensions, I think. Look here, for example, 7 millimeters from here to here. So it should be, half of the... Yeah, it should be, I don't know, maybe 5 times more or something. We'll see in a few seconds. So what I'm doing is, come on, 8. I surpassed this. My problem now is that I'm looking for something like a perfect symmetry, because we're looking to apply the mirror command. And in order to cut this model exactly in half, to make a mirror, we need to... Maybe this is the center of a symmetry. I don't know. It's not a mass center. The mass center is, I think, is here. but maybe I should use this edge somehow. How and what should we do? What should we do to properly split this plane? Of course, I can create an artificial segment and go towards the middle or something. 6.8. Yeah, I would like to lie on this edge, on this coordinate system. I don't know how it appeared. It's there. So 6.85, 7. Yes, and now I'm lying almost perfectly on this Z edge the Z axis that I see there. You know what? Let's split this body. Hopefully it will work. Split with this plane. And we get rid of this. Now we can do the mirror thing, yes? Mirror command, select mirror plane, and select this body. I usually uncheck create mirror relationships. And it's solid, but because we are in wireframe, we don't see it as a solid. Look here. It's solid. It looks almost perfect, but we're going to be convinced only when we are showing the teeth, yes? So this is the original jaw. Do you see where we're kind of displaced? Yes? This would mean we're going to mirror also the teeth, yes? So the teeth that exist on the right, we're going to mirror them to be the same like here. We're deleting the previous teeth which existed on the left side in order to ensure perfect symmetry below. This is what is this, for example? But this, what is this? We have two facets for the jaw. Let me save this as version 2. File save as version 2. Now I will delete these and let's go towards the teeth. You see now these teeth from the left side, they get out, but the teeth from the right side, they are correctly done. This means let's delete those teeth, all right? Let's hide the upper side. So these are not correct. They are not properly aligned. They are aligned to the previous left side of the jaw. So let's select them. Right-click, locate in structure tree. Right-click here, delete. And I will mirror these teeth. I will mirror them here, all right? A problematic thing is that there will be a collision here, but you know, there are already some collisions. Yeah, we're not going to use these as true teeth. We're going to fuse them, everything. In a future live stream, I will use proper teeth, separate with proper roots and everything. Let's not overcomplicate the live stream because we also need to go towards the FEA, and we're still on the modeling side. So let's do the mirroring of the teeth. Mirror command. This is the mirror plane, and we're going to mirror these parts. I said something about unchecking create mirror relationships. I don't care so much at this moment, because anywhere I will fuse everything in single part. You see, it's perfectly mirrored. This is why I wanted you to see the entire process and the tedious work and the hard work that needs lots of patience and knowledge, lots of patience and knowledge. And this comes after weeks and months and over white nights of unslept nights. So let me make this one part. Combine. While the operation is being made, let's see if we have a question, something. No. Perfect. So we have this one part. As I said in the beginning, the purpose is simulating the biting, the chewing. So we're not interested in the teeth at this moment. Let's show the entire geometry, and now we're going to fuse and merge everything on the upper side of the head. Yes, there is a problematic tooth there. We can choose the easy way in order to delete There are people without one tooth, yes, with a missing tooth. But what I'm choosing to do is, because let me undo. I will mirror that tooth, yes, the problematic tooth. Maybe this was the tooth. Let me mirror it. But we don't have a perfect symmetry. We don't have a perfect symmetry. We don't have a perfect symmetry. What should we do to ensure the merge of these parts? What? Triple click, select all. Let's hit again the combine command. That tooth will be excluded. The fourth tooth, all right. Let's look a little at this tooth. Why is it problematic? Since I kind of see some problematic faces here, also here, this one, yeah. Maybe it adds to our operation. What I usually do, I move it a little inside. So let's do something like this, 0.1. Nobody will notice. Do you think they are going to notice? Maybe they are not going to notice. So Control A. This is the beauty about biomechanics. We don't need to work with exact. So, and everything is one part, yes? We don't need to work with exact definition. 0.1 millimeter. In nature, it's not such a big of a deal. We have two parts, ladies and gentlemen. Yes? Let's save this. And let's go toward the mastication and everything. Now it's, at least the bottom part is kind of perfectly symmetric or mirrored. But because I didn't do the same, I didn't cut the skull and teeth with the plane, and I didn't mirror, there is not a perfect symmetry on the upper side. We don't care at this moment. What we care is something like this. Because there are some collisions here, yes? You can check these collisions, by the way. There is the prepare command. Always before doing a simulation, check for collisions. Always before doing simulations, check for collisions. Seriously, always. Let's close that geometry. Always check for interference, yes? Prepare interference. Look here, yes? We can solve this, and it will find the larger body. And at this moment, we don't know which tooth is larger than the other, the matching one, the touching one. So we're not going to chip our teeth, okay? We're not ruining our denture. Instead, we're simply going to pull this down, all right? Something like this. For example, again, let's check again for the interference, and we should have something here. Yeah, very small interference. All right. What we can do a little more, because there is, by the way, there is no perfect biting or resting of the upper teeth on the lower teeth, you know? There is always an overbiting or underbiting. Overbite, underbite. This is what I was talking about, yes? There is no, in nature, there is no perfect biting, yes? So let's also rotate this. I would like to rotate this, something like this. You see? Maybe 1 degree, let's see. From the keyboard, 1 degree. Ooh, it looks so nice. Maybe 1.5, because, yeah, I'd like to have the same distance, yeah? Here is a larger gap, and here is a smaller gap. So instead of, let's also rotate more, maybe 2 degrees, maybe. Let's see. Yeah, and let's go with this a little parted, because I would like to bite on a biscuit, and I'm thinking about the process of biting. So we'll start from here. These teeth, I think maybe they are canines, maybe. These teeth are very close to each other. Let's go something like this. I'm going to look for interference once again. Interference, prepare interference. There is no interference, hopefully. Ooh, there are some. Here in the back. And here. All right. Let's rotate this lower, the mandible. Let's rotate it, but how? We are going to rotate it as it is in reality. Never ever the upper side moves, never. Only and always the mandible moves. Never ever the upper side will bite or something. Only movement is the rotation of the mandible. If you didn't pay attention until now. So let's kind of construct an axis of symmetry here. Let's see how. We have a point here. I will create this. We have a vertex. I will create a point here. Let me move this point that I just created. You can see it here. Let me move it something like here in the middle of this, yes. And let's say that this is the axis of rotation, let's say. Yes, always look for this bone not to interfere with the skull. And yes, so we have a point here. What I would like to is move this point with control pressed. Hopefully it will work. Let's move it with control pressed on an axis, on the x-axis. And now we have 2 points, one there and one there. Why I need these 2 points? Because I would like to create an axis. An axis is perfectly defined by 2 points here, axis. This axis is the rotation axis for the mandible. So move the mandible. Let's name it. Why not? I like to name it jaw. This is why I wanted to make sure that also mandible is correct. Okay, jaw it covers everything. Jaw. Mandible move, and I will select, instead of the default maybe center of mass, what is here, I will go here, anchor, and I will select this axis. This means that I can rotate perfectly about that axis. Look here. So let's leave it like this and insert a biscuit or something to be bitten, or chewed upon. Do we have any question? No. All right. So can we look for a biscuit? Maybe something not so not so complex, because we already extended this bounce cream biscuit. Oh. This is too complex. I don't want to waste time with the mesh. This is pretty straightforward and nice. Maybe this one, maybe. Polyhedral something step. Oh, yes, downward. Let's like it. Double cookie. Do we need double cookie? Because of these points and everything, there will be a lot of editing work. And I don't want to waste time with editing. By the way, let's save and where is my biscuit? Is this the biscuit? Let's see. By the way, we resize the skull. Yes, this is the biscuit. Do we accept this biscuit? Do we accept it? Let's see if we can delete some of the rounds. We have these rounds. Can I delete them? It seems that I cannot delete them, and I don't want to wait too much. Let me just close this, and hopefully I saved the... Hopefully I saved this one. V2. Ah, we have this. Should we go for this? Should we or should we not? Yes, let's not waste too much time. For example, the diameter of this biscuit is around 57. This is a good diameter. It's realistic. Only I'm not convinced about the size of this skull. Let's measure 2 points, one from here and one from here, 2 vertices, and let's see the distance. 60 millimeters. So it's not possible. Let's make it 200. Yeah, 240, because I would like to scale everything 4 times. At this moment, I can delete the points and the axis. Let's leave the axis just for fun. All right, pull, scale, pick an anchor point. We don't care as long as we keep the anchor point for both parts. This and this with control pressed. And I will write from the keyboard 4. The scale will be 4, yes? Escape. Now let's measure again, and we should have something like 240, 243. Yes, millimeters, which is more realistic. Control S. Let's to save. Let's copy paste this. Copy and paste it here. Paste. Perfectly, almost perfectly aligned. Let's rotate it a little and put it in the mouth. Should we make it? Let's lie it on the upper teeth, something like this. Yes, and now let's kind of center it. Perfect. Should we make the biscuit bigger in order to be chewed by these teeth? You know what? Let's leave it like this. All right, and now this is why I left the axis, because I'd like to rotate now the mandible. Let's rotate mandible to bring it closer to the biscuit. Let's name it Biscuit. Biscuit. Mandible move. All right. As a reference, anchor, and we will select the axis. I lost the position of the axis when I scaled the geometry. No problem. We can move the axis here. We can move the axis here. All right. Something like this. It's not perfectly. We don't need a perfect orientation. Let's write 1 degree from the keyboard and see if we have. I don't see interference. Let's write 2 from the keyboard. Yeah, we begin to have collisions here. Let's move this a little upper. 0.1 maybe. I would like it not to collide with the upper teeth. All right, it doesn't collide, hopefully, with the upper teeth. Let's hide this thing and see if we have interference. Prepare interference. There are no interfering bodies. All right. So what I wanted is show all bodies. Maybe insert it more inside, more in the mouth. Let's use as an anchor this face because I would like to have this axis, something like here. Look here, something like this. All right, this means we need to change the angle of the mandible once again, and we're done. Anchor, axis, and let's, I don't know, maybe 355. It's the opposite. From 1, 2, or 3 degrees, it's minus 360, and this is why we need to come up with such pretty weird values. 358. Oh, yes. Let's leave it like this. So it looks perfect. Safe. Because I would like to go towards the simulation. Do we have interference here? Oh, I see interference here. Prepare interference. Yes, and only on this side. What do you know? This means there is an angle, a slight angle, horizontal angle, let's say. There is an angle here about the x-axis, let's say. Let's go again for the rotation. I will choose the anchor again, the x-axis, and maybe, just maybe, impose. It rotates the axis. All right. So move the mandible anchor axis, and let's rotate something like this. 359.5 instead of 360. Prepare interference. We're looking here on the right side to see if the interference disappeared or not. Now, at least now we have almost a symmetrical interference, and we can adjust the angle here. Yes, or maybe, yes, let's adjust it. Mandible, design, move, anchor, axis. We have the option also of moving it or adjusting the angle. If I adjust the angle, it will begin to bite the biscuit. Let's give it 1 degree, just 1 degree. We have very small interference, I think. Yeah, and we're beginning to bite the biscuit. All right, let's not continue with rotate. Instead, design, move, mandible, anchor, axis. Let's just drag it a little. 0.2, is it enough? 0.2, let's see. Let's see if it's enough. Prepare interference. Undo, and let's make it 0.5 from the keyboard, 0.5. All right, it begins to look nice. Here, I think we have an interference. Very small interference here. Let's use as an anchor this face because I'd like to move it. Yeah, from here. But we're losing something that I wanted in the past. Anchor here and something like this. All right, let's rotate a little the mandible and we're done. Anchor, ANSYS, and as I said, a little rotation. How much? 359, this means 1 degree. So here it looks nice, here always nice. And prepare interference. One interference. What do you know? Small interference here. All right. Let's move it once more, and we should be fine. How much should I go? 0.15 maybe. Prepare interference. The final movement, 0.1, right? Prepare interference. Come on. Oh my god, oh my god. Again, 0.1 maybe. Come on. Prepare interference. No error has found. This is what we wanted. Save. Right click, source, internalize all. Save. And we don't need this biscuit here. We're going towards the simulation side. So I'm leaving space claim open in order to quickly, for the geometry to be quickly inserted. Browse. Let's move it to my work folder. My work folder is so. I will copy from here and I will use it here. Control V. Let's copy the naming, open. I would like to use the naming here. All right, let's save this as stream 11. Do we have a space? We have a space here after the comma. All right. Very quickly, do we have a bone? A bone material? Let's see. I don't care about defining it. Let's see if I have it already defined. Bone. Oh yes, we have a bone. Look here at the properties. I defined some bilinear isotropic hardening, isotropic elasticity. Of course, we don't have steel. Only Iron Man should have, or Wolverine, they should have metallic skeletons. And the Biscuit. I'm curious about the Biscuit. Material properties. What? Come on, give me mechanical properties. Mechanical properties. Mechanical. No value. You're joking. Images. Ooh, we have Biscuit sample. Volume. Come on. What? Give me mechanical properties, please. So we have chemical, no. Wait, parameters, no. Come on, give me a density. We're wasting time, we're wasting time. We have a density here. Let's say 0.5. 0.5 gram per cubic centimeter cubic equals 500 kilograms per cubic meter. All right. So but what is the density? Let's duplicate this. F2 Biscuit, 500 kilograms per cubic meter. Young modulus. Does it have a Young modulus? Biscuit, Young modulus. It should be so small. 100. You know what? 300 megapascals. My Biscuit is 300 megapascals. And I think it's very brittle. Maybe the Poisson ratio should be 0.1, 15 to Biscuit Poisson ratio. It should be very brittle, 0.1, 0.2. Yeah, 0.10. You know what? 0.2 from me. Bilinear isotropic hardening. I don't care too much about the bilinear. Let's just ignore it. And let's leave it like this. Save. Double click. I didn't go inside regarding the Dentian mechanical properties, the pulp, the gum, the bone, the spongioside, everything, because we're looking right now in the beginning, we're looking at the kinematics of the mastication and the chewing of the food. And I would like for you to see the biscuit, how it's getting crushed, you know, between the teeth. So I'm starting basic, and then in the next live streams I will make the process more complex. It's easy to complicate things. It's very hard. It takes a lot of experience to keep things basic and fundamental and simple and very easy to understand. Let me check my smartphone. All right, no message. Full screen F7 for Zoom extents. Very quickly, we have skull, mandible, biscuit. Skull and mandible should have nonlinear bone. Why I'm using nonlinear? Because I stay away from unrealistic stress values. If we're using linear properties, we can have 1, 2, 3,000 megapascals, which is unrealistic because maximum values should be around 50, 100, maybe megapascals. Right? These are realistic values. These ones should have the mechanical properties of the biscuit. I don't care about connections. Let's delete them. Instead, frictionless, something like this. What I would like to do when having such irregular shapes, I would like to create virtual topology to unify more these faces. Yes. Let's go for medium. Right-click, generate virtual cells. So you see that the virtual topology united many of the existing patches. Here on the mesh, I would like to click here, smoothing low. Let's just right-click, generate mesh. Yes. I'm not interested about what happens here. I'm interested in the teeth to be a little more refined. Also the biscuit. The biscuit should have had some lacing, let's call it. I don't know. Let's make the biscuit to have tetrahedron elements. All right. I will create a section plane because I didn't check until now. I would like to see if the skull is hollow inside. Statistic 11,000 nodes. I like this. 11,000 nodes to have a quick solving with results during the live stream. Live results, you know. Oh, the skull is filled. Yeah, we don't care, just for fun, yes. I wanted to know it's filled. We don't care about this. We will care when we will deal also with brain and something else. All right, the biscuit. Let's make the biscuit. Let's assign it instead of the default 8. Let's assign it maybe 5, maybe. And Let's hide the biscuit with F9. Now I would like separately to select these faces. Sizing. I made a shortcut for the box select. Let's click this face. Control F to ensure that we select faces. Something like this. Maybe from above, maybe. Come on. Yeah. So these I would like to be final, all right? We start with the 5. Then let's right-click invert visibility. I would hide the biscuit because I need these faces. Come on, give me. Yes. Let me see if I can. No, it's not possible. All right, let me exclude those other faces, the big face surfaces, by going to single select. With Control pressed, we what? Yeah, let's say it's not so problematic. We should have had split faces here, but this is just a detail. Sizing, again, 5, yes. Let's right-click here, rename based on definition. Here, the same, rename based on definition. Right-click, generate mesh. Instead of 5, maybe we'll need to decrease the mesh size. Yes, because it's not such a big. We see those ridges from the biscuit. So let's assign 4 to the biscuit. Skull 3.3. Right-click, generate mesh. Do we have any question from the audience? We have questions. Josh Dagli, hey bro, can you please share the next slide for flexion extension of elbow with muscle? It's a very complex process, so it will not be so soon. So the modeling also the muscle is so much. Maybe in 2 or 3 months, maybe. Yeah, it's not in my pipe. Let's say in my future live streams. But you know what? Maybe spring, summer, maybe. Also, in your view, how to create proper contacts for ANSYS hyperelastic simulations. Also, how much time does it take for an average hyperelastic simulation? It depends on the complexity, on the mesh, and the properties. Proper contacts, yes, depends on how the parts are mated, if they are bonded or frictionless, frictional. Firstly, go with program control, then begin to edit them. You have check my other live streams because there are some details with nonlinear contacts, and also you have my solved FEA. You can look on them until in the next months when I will go for hyperelastic simulation. So, are you going to do spine as well? Yes, it is. It will be in the next 1-2 weeks because I would like to simulate the compression of a disc between 2 vertebrae. So it's in the pipe. It will be very soon made, yes. But the muscle with elbow and the bone much further in the future, because the muscle is also is complex regarding the modelization process and the material properties. Yeah, so I would like to draw your attention that I have something but without muscles. Until then, you can look here. Yeah, and this is what I'm working at in the background, because I'm also working. In order to present something live, you understand that I need to do it offline, let's say. And it takes weeks to solve this, knowing the fact that I'm also busy with other tasks and other problems. Looking forward to it. Yes, Hussein, you do some hard simulations on the channel. Yes, Hussein, thank you for noticing. Yes, it's very lot. It's a lot of hard work, and you can see in the live stream, it's a lot of hard work. And even though I'm doing some basic simulation offline, yeah, at home, it takes days and weeks until I simplify, and it looks very nice. But in the background, the work is so hard. And Mr. Josh Dudley, so yeah, please wait, stay tuned. Let's leave the biscuit as it looks like, because we don't care so much. The mesh on the teeth begins to look finer. Let's go even more, maybe 2.8. $13,000, $14,000. You know what? 2.3, and maybe this one 3 millimeters. Yeah, this begins to look very nice. I would leave the teeth and the biscuit. How many nodes does the biscuit have? Statistics 1,000 nodes. If I make the biscuit be meshed with 2 millimeters, let's see how many nodes does it add. Oh, it looks so nice. 3,500 nodes for a lousy biscuit, but it looks so nice. It looks so nice. You know what? Like this, because it will be nice for the crushing. Normally the biscuit should be meshed even finer, but I would like to have results. I would like to have results during the live stream. Let's leave everything as it is. All right, I will fix the skull, of course. Where do we fix it on this face? Yes, let it on this face, and this is all. We don't complicate things. I will draw your attention more towards the rotation of this thing. Connection, we have body ground revolute joint. Let's hide other parts. I will select here Control A, select all, because I would like to rotate the entire mandible, okay? And let's somehow correct. The rotation is kind of good because it rotates about the z-axis, but I would like to reorient this coordinate system to be better. For fun, the global coordinate system, where is it? Is Oh, it looks so nice. Oh, it looks so nice. Can I insert a coordinate system on top of the global one? Global coordinates. All right. So can I hide this just for fun? No, I cannot hide this. Why? Let me show what I want to do. These two are perfectly overlapped at this moment. Let's kind of offset them. All right. So, for example, offset. I can offset z with minus 30. I hope. Yes. Oh, and we're kind of perfectly where we want. Minus 33. Yes, it's around the rotation axis that we wanted. Should I leave it like this or complicate things? Let's leave it like this. I can sincerely keep the coordinate system as it is now because we are interested on the x-axis, and the x-axis is infinite. But for sure, for you to better understand, I will offset the coordinate system in order to be in the middle, just for sure, maybe with minus 45. Let's see. Yeah, something like this. Minus 40. Minus 35. Something like this. Almost in the middle, yes? And the x-axis is almost the axis of rotation. I'm thinking if I should bring this back on top, but let's use what we have. Here, as a load, I will assign joint load, revolute, type rotation, and let's assign. Firstly, we will assign an end time. How much should it be? Maybe for faster solving 0.01, even though it's kind of too fast. Why I want this value? Because I will use this value here. Tabular. And I'd like to rotate it. Oh, not on the... this is the default axis for the revolute joint is this one, which is not the one that I like. I'd like instead to use this axis from the coordinate system, yes? So let's go and see, defined by. Principal axis. Can I select the coordinate system that I created? No. Can I make this name selection? No. You know what? I think we are forced to go for the global coordinate. Instead for location. So I kind of created this without any purpose. I thought I could force it somehow in the joint. Where is the global coordinate system? The global coordinate system is here. But I need this offset. Let's remember, minus 33 on Z. Minus 33 on Z. What will happen if I make these 0? It will perfectly align. It does not perfectly align global coordinates. You know what? Let's use an easier approach. The easier approach is something like this. I will use two because we know the mandible is perfectly symmetrical, I will change the selection mode, the cursor mode, to vertex. I will select these two vertices and I will force the geometry to be something like this. Even though it's the z-axis is not perfectly aligned, let's force the z-axis. Click to change again. Again, the same vertices. It's not 100% perfection or something like this. But I wanted to have this axis. You see, the z-axis is this axis, and this will be the rotation axis of the mandible, and also of the rotation of the revolute joint. Look here, there is an asterisk inside, rotation axis z, and here we're going to rotate about this axis. It could have been better, but let's see what gives. All right. Can I delete this? I can delete this, but let's leave it for reference. Do we have any questions from the audience? We have. Looking forward. Yes, Mr. Hassan. Hello. In Explicit Dynamics, some cases I could not manage to use remote displacement boundary conditions in order to fix some faces. You have the fix command. Why should you use remote displacement? Instead I use displacement boundary conditions, but set 0, 0. Is it normal? N okay? Is it normal? Yeah, whatever floats your boat. Why not? You be creative. I usually steer. I very rarely use remote displacement. I almost always use simple displacement. But yes, remote displacement is also useful, especially when having rotational movement. Yes, do whatever you can in order to make the FEA work. There is no set recipe for everything. Be creative. Don't get stuck. Yes, use everything, and let's assign a value. How many degrees do you think there are from here to here? Do we have 3 degrees? Let's assign 3 degrees. So it will rotate upwards. Let me show something like this from this axis. All right, so let's go with the solving. This is what we all want to see. Nice results. Solution. Total stress strain. The biscuit is kind of in the air. I will not assign gravity. Should I assign a gravity? If I assign a gravity, there is a chance that the crumbles, the chips will begin to fall off. Just for fun, I will assign it, even though the FEA is done in such a short end time, we will not be able to see the effect of the gravity. This is my supposition. So, so we have a purpose for this coordinate system. Let's rotate it. Let's rotate it about x-axis. Yes. Let's rotate it with, I don't know, 60, 45, 45, 40, 30. Yeah, and we will have a gravity. Yes. Here we are going for the standard Earth gravity, and we will choose minus y direction. Look here, this is the gravity. In the event that the person stays stands, yes, because anyone can eat any biscuit at any given orientation. It's no mandatory position when eating, if we don't want crumbles to get in our nose or somewhere else. Let's leave everything at this moment kind of on default, except if we want the crumbling of the biscuit. Let's go here towards maybe 0.5. Output controls maybe 100 and save. Let's see if the cookie crumbles. Right. And how much time the solving will take. The first thing we can do is here for the energy, maximum energy error, make it 0 and rerun again. Maybe the mesh is too coarse. This is why we have the energy error, maybe. Clear generated data, solve. Repeat. Yeah, reply a detail for Hassan in the chat. I prefer to use joints. Rarely I'm going for remote displacement. I prefer to use joints. One hour. All right. The good news is that the FEA started to solve, but we need to decrease the 1 hour. All right. So look here, the time increment. Let's say time step is around 2.7 e minus 8. Yes, 2.7. We need to increase the time increment. So let's hit pause, because I would like to maybe go for 20 or 15 minutes maybe solving, all right? So I usually write here 1 hour, and I know that the solving takes 1 hour, and duplicate. Let's close this space claim. I have the desktop here. All right. So in a few seconds, the mechanical window opened. Let's decrease. The easiest way is to decrease the end time. But we also have the option of going for automatic mass scaling. And here, instead of -20, let's make it -6. And here, use 10 for maximum path scaling. Save. Solve. So instead of 1 hour, the FEA now takes how much? Solve again. Clear generated data, solve. And with patience, we will start solving the FEA. With lots of patience. Feel free to skip towards where you see results. Nobody forces you to endure what I'm experiencing now. So just skip ahead. Finally, let's see, instead of 1 hour. Ooh, 8 minutes. Yes, this is more like it. Perfectly. Now we're going for the part that we like, the part where we gather and watch for other people's work in order to learn more things. ANSYS, we're now for the ANSYS teeth, for example. Something like this. Let's see what other people have done. So this from Ozen Engineering, yeah, these are the how do you say, official partner for ANSYS. They are on the same place with CAD/FEM and so on. I'm not going there because they use separate teeth. I would like something like an overall. But you know what? Let's see just again in the next live stream. So this person is pushing. What gender? This engineer is pushing the implant, abutment, I think it's called. Bonded, contact, frictional. Yes, it's a nice FEA. Now I think maybe I should also do something similar. Ooh, it's so nice. You know what? I'm curious about the material. Titanium, maybe? Titanium. But the bone? What does he use for the bone? What? He goes for plastic for the bone. Yeah, the easy way. Yeah, why not? The easy way. Titanium alloy, non-linear. This is correct. Of course, this is correct. Yeah, except the bone. Yeah. We can see what happens in the thread. Yes. This is static. Ooh. So this is a pretty complex simulation. Yeah, it's not. It can be done much easier in Explicit Dynamics, but yeah, this is pretty complex, except the bone material. I think I will do something similar, but with a proper bone. Yeah. Nice work. So this needs to be taken into consideration. 6 minutes, all right. What is the tendency? What can we see here? I'm curious. Because I think 3 degrees is a little too more. But, oh, yes, it's nice. So we can see that only the mandible, the lower jaw, displaces. It didn't yet meet the biscuit. I think we need to increase the angle. Yeah? Yeah, we definitely need to increase the angle. Let's review a little the revolute joint again. I selected all the faces, all right. Let's stop and assign a bigger angle. We don't want to waste time, you know. 7, 10. Let's go for 10, and if it's exaggerated, we'll decrease it, no problem. Clear generated data, save and solve. This is why we need a pretty coarse mesh, at least in the beginning, in order to catch the feeling, to see the tendency of the simulation. How much does it go? Where does it meet the other parts? And if it does the job. If we would have used, as beginners do, they use mesh with hundreds of thousands of nodes and millions of elements, then we can expect results in 2030. It's unrealistic. At least in the beginning, we need to go with default, with coarse, to input, to evaluate many iterations of quick scenarios. After we're content, we're satisfied with the behavior of the simulation, then we can complicate the FEA. We can refine the mesh, we can assign a more realistic end time, and so on. But in the beginning, we're going to have coarse mesh, small end time, in order to ensure that the biting occurs, that the process is correct. So this is one of my simulations, and I will show it to you because it's unique. I didn't see it until now, made by anyone. So it's a file that breaks the nerve from the endodontic channel from. Yeah, I think I would remake it and also pull out the file. Now I think it needs to be also pulled out. The tooth is separate here. It's not fused with the jaw. It's very nice. It was a lot of work. Also obtaining the geometry of the file, and yeah, it was a lot of work. But it looks nice in the end. So this is what I kind of wanted to, something like this is what I wanted to do today. But here is, I think it's with separate teeth. Oh my God. Is it with separate teeth? Yes, they are separate teeth because they are differently colored. Only the roots, I don't think the roots are very well made, yes. It's something pretty rough. Yeah, it's not my best work, let's say. But here is much more complex, let's say, and this is very nice because we have nice roots and separate teeth. Look here, three roots for molar. We can see the pressure, the stress, the mesh is coarse for faster solving. Look how it pushes the teeth inside the mandible and the upper jaw. Yeah, it's nice. This is something from something pretty basic. I wanted to simulate the breaking of the lining of the, let's say, the pulp. There is like a pulp. Yeah, so let me show you. The tooth is surrounded, let's say, by this periodontal ligament. This is what I wanted to mistook for the pulp. The pulp is where the nerve is, all right? So when I extracted the tooth for the periodontal ligament to be broken, this is what I kind of wanted here, even though it's not perfect. But this periodontal ligament, you can see it here, is surrounding the tooth. Look here, yeah, and it's getting broken here while pulling out this was the purpose, to crush the periodontal ligament. Yeah, it's not a perfect simulation, it's kind of rough, it needs optimization. This is why I named it V1. There will be a V2, even nicer, even better, even, yeah, more satisfying in the future. Let's see the tendency. Oh, yes. So the biscuit is being crushed at 5 degrees. We are in the middle. And I'm interested if there will be holes and some bubbling. Let's wait a few more minutes. Where are we here? It's just implant. Let's see. Oh, what? So he did something in SolidWorks. Static. He's working with static. It's not so easy because there are multiple contacts. So should I dare go for materials? I think not. No. No. He's using the default steel. Let's see. Am I right? Titanium, but incorrectly written. Why I'm emphasizing this? Because we cannot dare to pay attention to very high and advanced parameters if we are going to have such slips, such small slips, all right? So we need to take into consideration anything and everything. Frictional with zero friction coefficient. So it's not frictional. It's frictionless. Frictional, no separation. Yeah. Force? What force? 300 newtons. 30 kilograms. Who is biting with 30 kilograms? How can you have 30 kilograms on one tooth? Just think about this, okay? So 27,000 megapascals for having for having linear materials. Look, what is this? What is this? He is not showing the scale. He should have shown the scale. No, he's not showing the scale. The scale is incorrect. It's higher. I think maybe it's 5 or 10 times the scale. What is this? What can we learn from this? Come on. All right. So I hope that person improved her simulation skills. Do we have something? We have biting, but we don't have crushing. Let's do something like this. Deformation and stress, but we will scope for the biscuit. Yes. Switch to automatic mode, and let's see the biscuit. Yeah, it begins to be crushed. Yeah, a small problem is the fact that we need to decrease the geometric strain limit. We need to make it around 0.25 or 0.3. We'll do it in 2 minutes. Do we have any question now? So, nice try. I hope this person improved. He has an entire channel with lessons. Let's see. What is this? This is very important to have almost half of the movie to have with the logo. This is very useful. Almost half of the movie. So we have rotation. Yeah, this geometry, I think I've seen it on GrabCAD, by the way. Very nice render. And where is the analysis? 4 months ago. 221 megapascals. Finally, we have some better values than 27,000 megapascals. So this person improved. This is good news. We have some geometry, something, but he doesn't show. Maybe here, yeah, here he is showing the process. Some other FEA? Huh? No. Huh? All right, so this finished successfully. So we have the first successful for solving. Let's remove edges in a wireframe and a little. Oh my God, it looks so nice. Because of the fast event, because of such a small end time, we have this, let's say, vibrations or something like this. You know what? Let's scope only the biscuit. Right-click, rename based on the finish, evaluate for results. Yes, so this is what we have. We can show the elements, no problem. Let's decrease the geometric strain limit, and you'll see the difference. The difference is very big. So here I will write here 7 minutes, and we will duplicate it So you can see from searching here, yeah, nobody goes for all the entire denture, for all the teeth, just a small abutment, a small tooth, a small, yes, nobody goes for big assemblies, for skull, for realistic scenarios. Look here, CFD. 2 parts, modeling dental implants in 2 parts, yes. This is interesting, yes. I was here and we can write here 0.5 strain limit, and here we will write 0.25 strain limit, or you know what, maybe 0.2 to be even more brittle, the biscuit to crumble even better and faster. So, quick reminder of one of my past simulations. Again, the rotation from this side. This was a chewing gum. Made in a static structure. At least it's an assembly, yes? It's not one part, one tooth, one abutment, one implant. Yeah, it's an assembly. We have more parts. The chewing gum is being compressed. All right, let's make, as I said, 0.2. Look here at the difference. In 7 minutes, we will see the difference. Yeah, and this is a little nirvana here. This is very nice. This is what I wanted to show today, something like this. Yeah. If you say, hey, Claudio, why do you come with the upper? We don't know what is upper. We don't know where the skull is. So this is an excuse, yes? We don't know if this is the mandible. Surely this is the mandible. And the person is eating upside down, all right? In order for the simulation to be correct. Yeah, with proper teeth. But what we're doing today is a basic scenario with the fused teeth fused in the jaws. It's very nice. It was a lot of work. The mesh is coarse, of course, for faster solving. The biscuit has 3 layers. Yeah, it has 3 layers. 1, 2, 3. We can see here, above, below, and there is in the middle there is the cream. It's yeah, it's very nice. So this person shows the entire process, let's say, 6 sections. Contact is in between. All right, this is a bridge. And he is pressing with two forces. He fixed here, he or she fixed. And the maybe stress in the bridge. No values. Why should you show the values? Also stress on bone. I tell you, of course, no values because why? Yeah, nice work. Why do you say teeth if it's tooth? And does it look like a tooth? Does it? What is this? Come on, why do you publish this? A force and fixed support, completion only support. So I hope you evolve, yes? This, they are working with discovery. Something more detailed there. For the example, let's see how the biscuit crumbles. It began this pretty big cavity, let's say, is due to the fact the cavity in the biscuit, not in the teeth, is due to the fact that we have a pretty coarse mesh. Yes, but we can see crumbling. I didn't fix the biscuit. I should have fixed the biscuit a little because it kind of dances a little due to the frictionless body interaction. I should have fixed a little the biscuit. But nevertheless, it begins to, you can see the teeth pressing, it begins to crumble very nicely. Firstly on the left side, then on the right side. Yeah, very nice. So what did they do here? They used ANSYS discovery. This is an optimized part in discovery. This is why you have such a organic, let's say, shape cut out. Yeah, also discovery. I have a similar simulation made. They are making such plates. Ah, that's all. All right. What will happen if we go for learn ANSYS in 10 days? Oh, this should be nice. If we go for mouth, let's see what will happen. Ah, one of my past simulations. This was made 10 years ago. Static structure. Also with fused teeth and jaw. I should remake this with proper teeth. We We can see the mouth guard, how it behaves. Yeah, it's a good start, I would say. Simulations we have seen in the past. This is something pretty nice. Here the skull is hollow as it is in reality. Vertebrae. Again, the teeth are fused with the jaws. It's needed because I wanted to show the impact between the leg and the skull, yes, and what happens on the vertebra, on the spinal level. This is why I didn't care about the teeth so much. Yeah, it's a very complex simulation. 1.8 minutes. And I have almost complete crumbling here. Yes, it looks very nice. We have complete success. So nicely done. Yeah, so nicely done. Let's look a little more, then we will close this live stream. Do we have any question from the audience? No, no other question. One person is resisting this. Yeah, it was a complex scenario, starting with modeling and with nice finished results. It was a complex scenario. Oh my God, it looks so nice. And to see it live, it's so nice. Let's remove the edges. So the FEA just finished. So let's animate. Yeah, it looks so nice. Semi-transparency, and here 0.1. Can we do it? Yes. All right. What will occur when we look in the section view? Oh my God, it's so nice. Let's animate. Yeah, very nice results. So yes, we learned a lot of things today regarding the modeling, discretization, the shortening of the simulation time, the crumbling, how to simulate brittle materials with brittle fracture. So from my side, that is all. A lot of new information I learned today. Yes, Hassan, thank you. Thank you for your efforts, and I'm looking forward for next tutorials. Thank you too for watching. Thank you for your time and patience. It's for your own benefit, and yeah, thank you for supporting me. Like watching these live streams, and yes, you can greatly improve your expertise in ANSYS workbench and more. So stay tuned because we can learn very great new stuff doing simulations in ANSYS workbench. Have a nice day. Thank you very much. Bye bye.